the speed of light, a constant that not only defines the limits of motion, but also dictates the rules of the universe we live in. It's fast, almost incomprehensibly fast, 299,792 kilometers per second. But how did we manage to discover something so incredible? What happens to matter when we approach that speed? And perhaps the most fascinating question of all, what happens to time when you travel at such extreme speeds? Get ready for a journey that will challenge everything you think you know about space and time. For millennia, light was a mystery that baffled some of the greatest minds in history. To early thinkers, it seemed obvious that light traveled instantaneously. Imagine standing on a hilltop and lighting a torch. The glow appears instantly, right? This led Greek philosophers like Aristotle to believe that light had no speed at all. It simply was. The idea that light could take time to move seemed absurd. But this assumption was challenged as our understanding of the cosmos deepened. The first major breakthrough came in the 17th century with Danish astronomer Ole Romer. While studying Jupiter's moon Io, Romer noticed something strange. The predicted eclipses of Io were sometimes late and sometimes early, depending on Earth's position in its orbit. He realized that this discrepancy wasn't due to Io slowing down or speeding up. Instead, the light from Io took longer to reach Earth when our planet was moving away from Jupiter, and less time when we were moving toward it. From this insight, Romer made the groundbreaking estimate that light travels at around 220,000 kilometers per second. It wasn't perfect, but for the first time, light was understood to have a finite speed. Fast forward to the 19th century, when technology and science were advancing rapidly. French physicist Hippolyte Fizeau refined our understanding with an ingenious experiment. He directed a beam of light toward a distant mirror and had it reflect back through a rapidly rotating toothed wheel. By adjusting the wheel's speed until the light beam was blocked by a tooth, Fizeau could measure how long the light took to make the round trip. His calculated speed was 313,300 kilometers per second, remarkably accurate given the tools of his time. But the puzzle wasn't complete. Scientists like James Clerk Maxwell laid the theoretical groundwork by describing light as an electromagnetic wave, showing that its speed was dictated by the properties of electric and magnetic fields. Then, in 1887, the famous Michelson-Morley experiment dealt a death blow to the idea that light needed a medium to travel through, such as the hypothesized luminiferous ether. Light, it turned out, could travel through the vacuum of space, and its speed was constant, regardless of the motion of the observer or the source. It was Albert Einstein who unified all these ideas in his special theory of relativity in 1905. Einstein proposed that the speed of light, exactly 299,792,458 meters per second, is a cosmic speed limit. Nothing with mass could ever surpass it. More astonishingly, this speed was absolute. It didn't matter whether you were standing still or moving at high velocity, light speed remained unchanged. This revelation forever altered our understanding of space, time, and reality itself. Thus, the discovery of the speed of light was not the result of a single eureka moment, but a journey through centuries of observation, experimentation, and radical thinking. Each discovery peeled back a layer of the universe's mysteries, revealing a cosmos bound by rules stranger than fiction. Now that we know how fast light travels, let's imagine what happens if you could travel at speeds close to this limit. It's simple in science fiction movies, but the reality is far more complex. Physics begins to change when you approach this barrier, and understanding it will challenge everything you know about the universe. The first thing to understand is that only massless particles can actually travel at the speed of light. For example, photons. The particles that make up light have no mass, so they can move at this incredible speed without needing infinite energy. Theoretically, this also applies to gravitons, which are thought to carry the force of gravity. But for anything that has mass, even a lightweight spacecraft or a simple atom, the story is different. Mass acts like resistance to motion. When you apply energy to accelerate an object, part of that energy is converted into more mass. This means that the faster you go, the harder it becomes to keep accelerating. For example, if a spacecraft reaches 90% of the speed of light, its mass would already have increased by more than double its original mass. If we try to reach 99.9% of the speed of light, the mass would increase by almost 70 times. The energy needed to continue accelerating at this point is so immense that, in practice, it's impossible to reach the speed of light. To surpass this barrier, you would need an infinite amount of energy, something that doesn't exist in our known universe. Therefore, while massless particles can travel at the speed of light, anything with mass is doomed to never surpass this cosmic limit. It's like trying to outrun your own shadow. But even if you can't reach the speed of light, traveling close to it causes bizarre phenomena. Space in front of you begins to contract due to Lorentz contraction. Light from the stars ahead shifts toward blue tones due to blue shift, while light behind shifts to red tones due to red shift. You'd be in a distorted universe where reality itself seems to twist around you. Now, we arrive at the most astonishing part of traveling at extreme speeds: time. Time, which seems constant in our everyday lives, is actually something flexible and shaped by how fast we move. This is the essence of Einstein's special theory of relativity, and the results are as mind-boggling as they are fascinating. Imagine two identical clocks. One is aboard a spaceship traveling at 95% of the speed of light, and the other stays on Earth. To you on the spaceship, everything seems normal. Time ticks by regularly. But to an observer on Earth, your clock is ticking much slower. This effect is called time dilation. For instance, if you spend 5 years traveling through space at near-light speeds, you could return to Earth and find that 50, 100, or even more years have passed. For you, time seemed normal, but for those on Earth, it continued at its usual pace. This phenomenon is illustrated by the famous twin paradox. Imagine twin brothers. One embarks on a space journey at near-light speeds, while the other remains on Earth. When the traveling twin returns, he may have aged only a few years, while the twin on Earth may be decades older. For the traveler, it's like a journey into the future. This isn't just theoretical, it's been experimentally verified. In 1971, scientists used atomic clocks on commercial flights around the world. When the planes landed, the clocks were compared to those that stayed on Earth. The result? The clocks on the planes showed slightly less time had passed. Time dilation is real, and time dilation doesn't just occur due to speed. Gravity also affects time. The stronger the gravitational field, the slower time moves. Near a black hole, for example, time would almost freeze compared to someone far from that gravitational pull. This flexibility of time reveals that the universe is far more complex and fascinating than we imagined. Time isn't a straight, constant line. It's an elastic web shaped by speed and gravity. If we ever develop the technology to travel close to the speed of light, we could explore the cosmos and leap into the future simultaneously. Time dilation offers a sort of natural time machine. The question remains, what will we find when we get there? The speed of light, the limits of physics, and the dilation of time all show us that we live in an extraordinary universe filled with mysteries we are only beginning to unravel. Exploring these concepts isn't just a scientific journey, but a quest to understand the very nature of reality. If you enjoyed this exploration of the frontiers of science, leave a like, subscribe to the channel, and turn on notifications so you don't miss more content like this. And now, I want to hear from you. If you could travel at near light speed, where would you go? Leave your answer in the comments. Until next time,